All right. I'm going to be talking about a topic from linear algebra. This is one of the very important topic, and that would be dimension of a finite dimensional vector space. I'm going to be explaining certain things and then prove some of the theorems in this topic. I know that the intention will be to define what is a dimension. But before I do that, I want to first of all pose this theorem because it is very important to understand this theorem before we give the definition of dimension of a vector space. All right, so I'm just going to pose it as a theorem. And it says any two bases for a finite dimensional vector space just call it V. The same length. When I say length, I mean the number of vectors in the basis. All right, so let's prove this very quickly, and then I will proceed to define what is a dimension of a vector space. Okay, the assumption is that we have a finite dimensional vector space. So let's suppose V is finite dimensional. Okay. And any two bases. So let's represent the first basis to be B1 and the second basis to be B2. The goal is to prove that B1 and B2 have the same length. Okay. Since B1 is a basis, it is linearly independent. Remember that a basis for a vector space spans the space and is linearly independent. So B1 is linearly independent because the basis for V is linearly independent set in V. Okay. And B2 is a basis, so B2 spans V. All right, so previously we talked about the linearly independent set and spanning set. And the theorem was linearly independent set, the length of linearly independent set is less or equal to the length of the spanning set. So if B1 is linearly independent set in V and B2 spans V, then the length, this implies that the length of B1, the linearly independent set, is less or equal to the length of B2, the spanning set. Okay, now let's take it to the other direction. All right, the same way, B2 is a basis, so it's linearly independent set. In V. B1 is a basis, so it also spans V. Using the same theorem that I just used previously, it means that the length of B2 is less or equal to the length of B1, since B2 is linear independent set and B1 is spanning set. All right, and so we can conclude. So the length of B1 was less than the length of B2. Now the length of B2 is less than the length of B1, and length of B1 is exactly length of B2. What can we conclude from here? It means that if any basis for a vector space, of course, basis is not unique. So any basis of a vector space must have the same dimension. It has the same length. All right. Now that we understand that it doesn't matter what basis I take for a vector space, as long as the basis, the length is going to be the same as for the rest. All right, so let's formally define now what is a dimension. So dimension. Of a finite dimensional vector space is simply the length of any basis for the vector space. And since we know that all bases have the same length, so it's not ambiguous to say that this makes sense. All right. Just to recall certain examples, classical examples, very briefly. One, whenever the set is empty, when we have a vector space with just zero vector, then we say that we denote, say that the dimension of V is 0. All right, so in general, we denote, notation-wise, dimension is denoted as dim of V. So instead, in this case, I will just say dimension of V equals to 0. So V has just single set 0 vector, and so the dimension is 0. I want to remark something here. Anytime I want to prove that a vector has only 0 element, if I can show that the dimension of that vector is 0, then the vector has 0 element. And the same way, if a vector has 0 element, then the dimension is 0. Right. 2, if I'm talking about Fn, Fn here is defined to be either Cn or Rn. The dimension of this vector space is n. And the simple reason is because the standard basis here, for this is given as E1 up to En, where Ej is 0, 0, 1, 0, 0, and this one is in jth position. So for example, E1 is 1, 0, 0, all the way to 0. Okay? And there are n, the length of this set is n, and that's why we have dimension to be n. All right, so if I'm working with a vector space of all polynomial of degree less or equal to n, which we write this way notation-wise, the dimension of this vector space is n plus 1. Again, why the simple explanation for this is because standard basis also for this vector space is given as 1x squared all the way to x to the n. And there are n plus 1 vector element in this. So the length is n plus 1. Okay, so number 4, if you are dealing with set of m by n matrices, which of course we show that is a vector space, the dimension of this is just the product of the order, so m times n. You can also simply provide the standard basis, which is similar to that of Rn when you make it as a matrix. All right, so now that we have the general idea, let's then look at some very important theorems in this topic. Okay, so the first one I'm going to be talking about here is a very important theorem. So the theorem says, suppose V is finite dimensional, then every linearly independent set of vectors in V with length dimension V is a basis for V. All right, so first, let's understand what the theorem is saying. So whenever I know that V is finite dimensional, and I have a set that is linearly independent in V with the same length as the dimension of V, then that set is a basis. Okay, so let me reword that. To show that a set is a basis for V, you need to show two things. One, that it spans V, and two, that is linearly independent set in V. But this theorem is saying, if I know that V is finite dimension and I have a set that has the same length as the dimension of V, I do not need to bother myself. All I care is to show that that set is linearly independent. Once it is linearly independent, it's going to be a basis. So I don't have to show that it spans the space. So let's prove this theorem. First, whenever we say V is finite dimensional, what we are saying is that dimension of V is less than infinity. Okay, so we have this. All right, since we have this, let's denote the dimension of V to be n. Okay, it's finite dimensional. And since the set that is linearly independent set in V has the same dimension, so let's take a set, let's call it V1 all the way to Vn, linearly independent sets. linearly independent set. In V. Of course, the length of this set is n, so the dimension the dimension of V also has to be n. All right, now remember that based on our previous lecture, we spoke about whenever I have a linearly independent set in V, I can always extend that set to a basis for V, provided B is finite dimensional. So in this case, since B is since B is linearly independent, we can extend B to a basis for V. We can extend B to a basis for V. Okay, but according to the definition of a basis and dimension, since dimension of V is n, then the length of, so let me write that, since dimension of V is n, then the length of a basis for V is n. All right, so I have a set, linear independence in V, and I want to extend, the theorem says I can always extend that to a basis for V. But here, the basis for B, or any basis for V, must have the length n. It means, it implies that this extension is the trivial extension. That is, I basically had nothing. And so B has to be a basis. Okay. The key here is the theorem that we've studied before that says, when I have a linear independent set in V, I can always extend it to a basis for V. We've proven this already, where we dealt with the topic under basis, okay? All right. Now, let's go to the next, the other side of this. Okay, so we now know that every linear independent set in V with the same length, with the dimension of V is a basis for V, provided V is finite dimensional. This same idea is true when I have Spanish set in V with the same dimension of V. The length is the same with the dimension of V. So let's quickly go into that. So this is the theorem. It says, suppose V is finite dimensional, then every Spanish set in the vector V with length dimension V is a basis for V. This, the idea of the proof is similar to the one we did before, okay? So let me quickly do the proof, similar to the one we have. So first, dimension of V is n, so let that, and let's all say that B, which is V1 up to Vn, okay, is the spanning set, okay? Spans V. All right. The same theorem that we've seen before says anytime I have a spanning set in V, a set that spans V, I can always reduce that set to a basis for V. So since the span of V is V, we can always reduce V to a basis for V. Oh, now dimension of V is n implies that the length of any basis for V is n. Again, this is a trivial reduction. Hence, B has to be a basis for V. Okay, so very interesting. But from now on, I know many of my students have been asking, can we take the advantage of this idea? I said, we are yet to prove the theorem. Now we've proven the theorem. So when you know that if a vector space is finite dimensional and you are given a set that is linearly independent, and you check the length of this set is the same as the dimension of the vector space, you do not have to prove anything to show that that linearly independent set is a basis. So it's the idea of not letting us prove two things every time we want to show that something is a basis. One is enough. Whenever the dimension of V is the same as the length of the set we have. And of course, V has to be finite dimensional. All right, so we are now in a very important concept in dimension of a vector space. And that has to do with dimension of a sum. When I have, we talked about sum of two subspaces before, and we discussed a lot about that. We even went to the extent of talking about direct sum. Here it is not a direct sum yet, it's just sum of two subspaces. The question is, when I have two subspaces of a vector space, dimension of the sum is equal to the dimension of the first plus dimension of the second minus the dimension of the intersection. We need to prove this. So I want you to pay attention here. This is a very important theorem when it comes to linear algebra in general and dimension in particular. So proof. All right, so let's start from the intersection. Okay, so remember that the intersection is a vector space, so we can take a basis. So let's start with the basis for the intersection. And let's call that U1 all the way to UN, okay? Be a basis for U1 intersection U2. Okay. The moment I take a basis for this, it implies directly that the dimension of the intersection, all right, is the number of vectors in the basis, so which is m in this case. Okay. If it's understood to this extent, the next thing is, remember, B is a basis, so B is linearly independent. So let me start with, since B is linearly independent as a result of being a basis, use the same theorem that I previously used. We can extend this to a basis of U1, okay? Basis for U1. Okay, not just for U1, we can also extend it to a basis for U2. And you should ask a question here, why can we do that? Okay, the reason is that U1 intersection U2 belongs to U1, and U1 intersection U2 belongs to U2. So that gives us that idea because it belongs to that, okay? So we're now having basis for the intersection, which is now linearly independent. I can always extend it to a basis of the bigger set, okay? Now for U1, let's call the basis we just got B1. And that is going to be, we start with the element in B first. So U1 all the way to UM. And then I'm going to add more elements, which I call V1 all the way to VI. Basis for U1. And similarly, I'm going to do that, start with the basis element in the basis of B and augment it with some other vector. Let's call it W1 all the way to WN. Again, I'm extending means I have some element to the basis. Let's say those elements are this, okay? All right, now we have something that is 9. Again, let me recall what I've done so far. I started from the intersection. I take a basis for intersection and I show, so U1 intersection U2 is a vector space, so there is a basis. So I take B as a basis and I have the dimension of this U1 intersection U2 to be M. And I extend this basis to a dimension, to a basis for U2 and U1, since U intersection is containing each of them, the sets. All right, now I want to make a very serious claim. I want to claim something, okay? I want to claim that actually this set that I'm about to define, and it combines everything that we've seen. So I start with U1 all the way to UM, and I include the vector I added for U1, I include the vector I added also for you to. I'm claiming that this is a basis for the sum U1 plus U2. It's a claim yet, I've not proven that it's true. All right, so let's show that it is true. We have to show two things, that this is linearly independent and it spans, is a linearly independent set in U1 plus U2 and it spans U1 plus U2, okay? All right, so let's start from the span. Okay, so to show that something spans the vector space, you take an element from the vector space. So let's say we take W, okay, from the sum. We need to say if we can write W as a linear combination of elements from U1 plus U2. But whenever I take an element from the sum, what does it mean? It means this implies that there exists some vector in U1 and some vector in U2 such that W is equal to U plus V. That's exactly how we define the sum of two subspaces, okay? So we have U1 is in U is in U1 and V is in U2, meaning that W is U plus V. All right, but don't forget, when I take an element from U1, what does that mean? Remember that B1 is a basis for U1. It means that I can write any element in U1 as a linear combination of the element in the basis. So this simply means that there exists some constant, okay, let's call it A1 all the way to AM, and that's part for the U part in that set. So let's say B1 all the way to BR. Scalars, okay? There is this guy such that I can write U as a linear combination of the vectors in B1. So A1, U1 plus all the way to AM, UM plus B1, V1 plus all the way to BR, VR. So remember that B1 is a vector containing, it's a basis for U1, which contains U1 all the way to UM, V1 all the way to VR. And B2 is a vector containing U1 all the way to UM, then W1 all the way to WN. All right, so I have this for U. Similarly, I should have for V because V is coming from U2. It also means that we have some constants which could be different from the one we had before. So let's take C1 all the way to CM and D1 all the way to DN. This signifies the numbers we have here. So let's take it as a scalar. F here is either C or R. So such that I can write V as a linear combination of the vectors in B2. So that would be C1U1 plus all the way to CMUM plus D1W1 plus all the way to DNWN. This is perfect, right? So we are just using what we have. I take a W in the sum. It means that I have some vector in U1 and some vector in U2 where W is the sum. Now, a vector is coming from U1 means that I can write a linear combination this way. A vector is coming from U2 means I can write a linear combination of the element from the basis for U2. So now that we know how to write U and V, what is now W? So we can now write W, which is U plus V. Instead of U plus V, let's put the linear combination. So it will be A1V1, A1U1 plus all the way to AMUM plus B1V1 all the way to BRVN. Sorry, this should be VR. This should be VR, this should be VR. Then I'm going to add, this is the U part. I'm going to add the V part. So C1U1 all the way to CMUM plus D1W1 all the way to DNWN. Now, notice that I have some U's, I have some U's the same. So what that means is that I can combine those with, so U1 is here, U1 is here, so I can combine those constants there. So A1 plus C1, U1, and I can do that for all the terms that concerns U high for some I between 1 and M. So this will be AM plus CM UM. And the other ones, they are not the same, so I just keep them the way they are. So B1, V1, all the way to BR, VR, then D1, W1, all the way to DNWN. Okay. I started with a vector in the sum, and I'm now able to write it as a linear combination of the vector from B star. You can see that this U1 up to UM is a vector, is a part of B star. And V1 to VR is also in V star, B star. And W1 to WM is also here. Anytime you take an arbitrary vector from a vector space and you're able to write it as a linear combination of some vectors from a set, then that set spans V. So we can conclude that span of B star is exactly U1 plus U2. So one part of B star being a basis is proven. Now let's go to the second part. Okay, let's show that it is linearly independent. So second part, to show that it is linearly independent. For us to show that B star is linearly independent, we just need to suppose there exists, okay? Suppose there exists some constants enough to cover all the elements in B star. So let's follow the same notation. It could be different ones. So A1 to AM for the part of U, B1 to BR for the part of V, and D1 to Dn for the part of W. So we have this scalar such that A1 U1 plus all the way to AN UM plus B1 V1 all the way to BR VR plus D1 W1 all the way to Dn Wn is 0. We suppose there exists some constant like this, such that the linear combination with the vector element is 0. And all we have to prove, we need to show that all the constants, all the scalars are 0. We need to show that all the scalars are 0. Okay. All right, so from this equation, let's send this guy to the other side. So I'm going to simply have A1 U1 plus all the way to AM UM plus B1 V1 all the way to BR VR will be equal to minus D1 W1 minus all the way to minus DN WN. And if you really want to write this nicely, you can simply write minus and D1 W1 all the way to DN WN. All right, now take a look at what I just wrote. Take a look at what I just wrote. This guy here is coming, it's a linear combination of the vectors element in B1. Okay, so this is in U1. Now look at this guy. It's a linear combination of some elements in U in B2. Now you may want to say, oh, but it doesn't have some of the other vectors. Yes, take the constant to be zeros for those ones. Okay, because B2, remember that B2 is going to be, B2 is some U's, then some W's. And to see that this guy is the linear combination of all these guys, simply the constant that we multiply U1 to UM, take them to be 0. So it is very clear that this guy is in U2. That's a combination of these vectors, and this thing spans U2. All right, I have something that is in U1 is equal to something that is in U2. Automatically, that gives me an idea, okay? If something is in U1 and is equal to something in U2, it means that either left or right is in the intersection. So, but I'm interested in the right. So it means that this guy here is in U2. So D1 plus all the way to DNWN as a vector belongs to U1 intersection U2. If the set is in U1 is exactly equal to a set in U2, it means that either left or right belongs to the intersection. So or maybe simply you can include the negative sign, okay? Now, I know who is the basis for U1 intersection U2. Any element I pick in U1 intersection U2 I should be able to write it as a linear combination of the elements in the basis. So this then implies that this guy, which is a vector, just look at it as a vector. So D1, W1 plus all the way to Dn, Wn can be written as some linear combination of the vectors in the intersection. The vectors, the basis for the intersection is simply all the U's. So I'll just use C1, U1 all the way to Cn, Un. Again, I want to explain this because it could be confusing. Since this side and this side is equal, and one side belongs to U1, one side belongs to U2, it means that either of these vectors, they belong to the intersection. So let's take the right. If the right is in the intersection, it means I can write it as a linear combination of the basis element for U1 intersection U2. The basis element I chose at the beginning of this proof is just U1 all the way to Um. So that's how I get to this line here. Now, let's collect everything to one side. It means I can bring this negative to the other side. I have C1 U1 plus C all the way to CM UM. All right. Then when I bring those one, it becomes positive. So D1 W1 all the way to Dn Wn equal to 0. Oh, look at this equation very well. It's a linear combination of the element of the basis B2. Okay, this is a linear combination of the elements of the basis B2, and basis B2 is the basis for U2. Now, B2 is linearly independent, so when I take a linear combination like this equal to 0, automatically gives me that all the constants are 0. So C1 equals all the way to Cm equals D1 all the way to Dn equal to 0. So all the constants are 0. And this reason for this is that B2 is linearly independent sets. All right, I'm saying much than I'm writing, so it would be nice to take note from what I say. All right, so B2 is linearly independent, so this kind of combination equal to 0 must give us that all the scalars are 0. Okay, we are not done. All right, you know that in this equation, let's call it equation star. In this equation, we now have that all the C's, all the D's are 0. So basically, we are saying that we don't need this term again. So star now, equation star will become, star becomes, when all the C's are already 0, what will be left is A1, U1, all the way to AM, UM, then the term for V. So B1, V1, all the way to BR, VR equal to 0, because the terms of C's are now all zeros. Okay, again, look at this equation. This sounds like, it looks like vectors, exactly the vectors in B1, okay? And since B1, okay, since B1 is also linearly independent, is a basis, so it's linearly independent, it means that all the constants are 0. And that's what we want to prove. We have shown that when we take linearly independent sets, let me just restate that. We have shown that if A1U1 plus AMVUM plus B1V1 all the way to BRVR plus D1W1 all the way to DNWN is 0. If this equation is 0, then A1 all the way to AM and B1 all the way to BR, D1 all the way to DN are all 0. Hence, since all these are vectors in B star, as B star is linearly independent. We've shown now that B star is linearly independent before we show that B star spans U1 plus U2. We can conclude now that B star is a basis for U1 plus U2. Okay, we are not done. we just showed the claim. Now let's go back to what's the dimensions that we need. Let's go back to the dimension, okay? I'm going to restate everything we've provided. So we've shown that B, we have that B all the way to this is a basis for the intersection, which means that the dimension of the intersection is M. We have shown also that the basis B star, which is U1 all the way to UM, V1 all the way to VN, VR, W1 all the way to WN is a basis for U1 plus U2. This means that the dimension of U1 plus U2 will be how many elements here? There are M elements here, plus there are R elements here, and there are N elements here. So let's write that. So dimension of U1 plus U2 will be M plus R plus N. All right, so the dimension of so this is what we have. But remember that we can rewrite this equation nicely actually. So M plus R okay, plus M plus N. Now I invented one N, okay? And that M I'm going to, so simply add and subtract M, okay? And if you look, this is the dimension of U1, because the basis for U1, so maybe that it would be nice to write that out. So B1 is U1 up to UM, V1 up to VR. It's a basis for U1. And B2 similarly is U1 up to UM, and W1 up to WN, basis for U2. So the dimension of U1 is going to be M plus R. The dimension of U2 is going to be M plus N. And the dimension of the interception, we already see it here to be M. And that is the end of the proof. That is the end of the proof. And this proof that we started. It's a very important and fundamental theorem when it comes to dimension. Okay, so just have a couple of more questions to answer and I will be done with this video. All right, so let's look at some examples now, okay? Suppose I have U and W, they are subspaces of R8, such that dimension of U is 3, dimension of W is 5, and U plus V is equal to R8. We want to show that the U intersection W is just a zero vector. That's just one singleton zero. All right, so let's prove this. Okay, now just what we just proved, the theorem we just proved, we know that dimension of U plus W, in this case, is the dimension of U plus dimension of W minus dimension of U intersection W. This we have just shown. Now, dimension of U plus W is the dimension of R8, which I already gave you. Dimension of Rn is n. So dimension of R8 is 8. So left-hand side is 8. Dimension of U is given to be 3. Dimension of W is given to be 5. And all we don't know yet is the dimension of the intersection. But this is 8, okay? If you subtract from both sides, this eventually gives you the dimension of U intersection W. Excuse me. Dimension of U intersection W is 0. Remember when I gave the definition, when the dimension of the vector space is 0, it means that that vector space is 0. So it means that U intersection W is just 0. Okay. I think the proof is fairly straightforward. So let's go to the next example. Also, we have U and W, they are 5-dimensional subspaces of R9. We want to prove that U intersection W is not 0. Okay. All right, just one comment in the previous example. Because of this situation, we can conclude that R8 is actually the direct sum. of u plus w because the intersection, okay, is 0. When you have the intersection to be 0 and R8 is already the sum, then that is going to be a direct sum. In this case, that's not. So U and W are subspaces with 5-dimensional. With dimension 5, it means that the intersection is not 0, which means that R9 cannot be direct sum of U and W. So let's quickly prove this as well. All right, so let's use the same theorem. Dimension of U plus W, okay, should be dimension of U plus dimension of W minus dimension of the intersection. All right. We don't know what is dimension of U plus W, okay? We are not given that the sum is R9, so. But we know the dimension of U is 5. The dimension of W is 5. We don't know the dimension of the intersection as well. So let's keep them as they are. So this is 10 minus dimension of U intersection W. Okay, that's all we know for now. But we know, even though we are not given the fact that U plus W is equal to R9, we know that U plus W is a subset, perhaps maybe the entire R9, but it's a subset. Based on the previous theorem that we know, if I have a set that is a subset of another, the dimension of the smaller set, already shown this one before, so I didn't include it in this presentation, is less than the dimension of the bigger sets, okay? And what does this mean? I know the dimension of R9 to be less than, sorry, to be equal to 9, all right? If the dimension of the sum is less than 9 or equal to 9, it means that suppose I have that minus now. So minus dimension of U plus W will be bigger or equal to minus 9. Just refer the inequalities. Now let's come back to this equation, this one. I have the dimension of U plus W is equal to 10 minus dimension of U intersection W. All right, so I just want to do arithmetic there. I bring in dimension of U intersection W to the left. And what I have in the right will be 10 minus dimension of U plus W, okay? But I know that this guy here is greater than or equal to minus 9. So everything here will be greater than or equal to 10 minus 9. And 10 minus 9 is 1. So what I've shown here is that dimension of U intersection W is bigger or equal to 1. Is not 0, that is implication. And since I'm sure that dimension of the intersection is not 0, I can conclude that the intersection is not a 0 vector. That's proof the theorem. Remember that if intersection is 0, then the dimension will be 0. But here we've shown that dimension of the intersection is bigger or equal to 1. It means that the dimension is not. The intersection is not a 0 vector. All right, let's look at another example. Okay, so let B equals V1, V2. Okay, set of V1, V2, where V1 is this and V2 is this. Show that B is a basis for F2. Ordinarily, without this lecture, you could have simply show that this B is linearly independent and it spans F2. But now that we know, we have the idea of some of the theorems I'm just proving, remember here that the length, okay, so solution. The length of B here is 2. There are 2 vectors in B. The dimension of the vector space we are working with F2 is 2. Because these two agree, we can say that it's enough. It is enough to show that B is linearly independent or B spans F2. It's enough to show either of the two, okay? You don't have to show both of them. But clearly, when we have two, I spoke this before in my previous lecture. I said when you have a set containing two elements, if one is not the multiple of the other, then that set is linearly independent. Clearly, okay? V1, which is 5, 7, is not a multiple, or let me say a scalar multiple of V2, which is 4, 3. There is no constant you can multiply with V1, which is 5, 7, to get 4, 3. And there is no constant you can multiply with V2, which is 4, 3, to get 5, 7. And whenever you have that, then B is linearly independent. And by the theorem we know before, B is a basis for F2. All right, because of the time, I will stop here, and I will see you in the next video. If you watch this and you like it, make some comments below. And if you have some questions, also ask your questions. I will try to give some feedback. I hope this helped my students, and I hope it helps every other person watching it. Thank you very much. Hope to see you in the next video.